In support of OGC's advancement of the GIMI standard and the imagery domain ontology, Voyager's contribution to the testbed is identifying and connecting the standard's imagery files with the descriptive corresponding metadata files, making GIMI data easier to discover, interpret, and act on. Despite the power of GIMI and related formats, their value is often difficult to realize in practice due to fragmented file structures, highly technical metadata, and the manual effort required to connect, interpret, and validate the data. Within the GIMI standard, a HIFE image and its TTL sidecar metadata normally live as two disconnected files. Voyager indexes both and establishes the relationship between them with a focus on both lineage and provenance. In Voyager's platform, a pipeline defines how content gets enriched during indexing. So what gets represented, how it gets transformed, and what metadata gets surfaced. For Testbed-21, we configured a pipeline step explicitly for GIMI content. This is the step that does the linking. When Voyager encounters a HIFE image file, it looks for a TTL sidecar file with the same file name. When it finds one, it reads the TTL, extracts the metadata, and associates it directly with the image. With our pipeline ready, we can point Voyager to the GIMI content. Voyager has connectors for file systems, S3, and other content repositories, so it doesn't matter where the HIFE data is stored. We can index it wherever it happens to live. We're using a folder here for simplicity, but the process is identical for any type of repository. We'll give this one a name and point it to the folder where our GIMI files are stored. We also have the option to filter by file type. If you have a mixed folder and only want to index HIFE files, you can specify those extensions, and Voyager will skip everything else. It's a useful capability when you're working with large, diverse datasets. For indexing, we're also leveraging libHIFE, an open-source GIMI decoder. These are community foundations that Voyager builds on, not replaces. GIMI supports both still images and video at varying resolutions, and some of these files can be quite large, so indexing time matters in real-world workflows. Our platform is designed to handle large files efficiently. In terms of lineage, to make the relationship between imagery and metadata visible at a glance in the Voyager platform, the TTL appears as a component file of the format on the detail page. We'll show you what that looks like now. Here we see our initial results of our 24 index testbed files. The thumbnails of those files are here in the center, properties of the files are on the left, and there's a map view on the right. What you're seeing here on the details page is metadata pulled from both files working together. The TTL sidecar contributes the spatial context, coordinates, bounding box, and sensor metadata. In the metadata details, you can see both the HIFE image file and its associated TTL sidecar linked together. The HIFE file contributes the image properties, geometry, number of spectral bands, pixel depth, and image dimensions. Voyager extracts from both and surfaces it in a single analyst-facing view. As a quick example, 3 bands typically means standard RGB imagery, while higher band counts often indicate multispectral or hyperspectral sensors, capturing data beyond the visible spectrum. This isn't just raw file properties. It's the information an analyst needs to actually understand what this image shows and whether it's useful for their work. Indexing and visualizing content inside Voyager is useful, but it's not the end goal. The goal is that GIMI data is queryable and discoverable by systems that have never heard of GIMI. This is our OGC API Records implementation. The same index GIMI content that we've displayed in the Voyager platform is also available as a standards-compliant endpoint, queryable by any external catalog, portal, or OGC-compliant tool. You can also access OGC API Records JSON response for the current search result set. Alongside this, we're exposing the same content through STAC, the spatiotemporal asset catalog standard, widely adopted in Earth observation workflows. The two standards are complementary. STAC is purpose-built for spatial and temporal content, while OGC API Records is the broader layer, covering everything STAC handles, plus non-spatial content like documents, reports, and non-georeferenced files. Ultimately, building on open standards isn't just a technical choice. It's how we ensure GIMI data can outlast any single tool, organization, or workflow, and remain useful to the broader community. Under the hood, Voyager is using GDAL OGR to extract geospatial information from the GIMI content. These open-source geospatial libraries, maintained by the OSGeo community, are widely used across the industry. libhife handles hive decoding, and we want to specifically acknowledge Dirk Farron, a contributor in both Testbed-20 and Testbed-21, who built a libhife and a hive generator that we use to expand our test content library. So just to summarize, the problem we started with was that GIMI files and their metadata don't connect themselves. What you saw today was our team at Voyager working to close that gap, linking the imagery to its sidecar, surfacing it in a way analysts can actually use, and making that same content available to any compliance system through open standards. The data doesn't have to live in Voyager to be useful. It just has to be findable, readable, and connected. And that's what we built, and that's what we'll continue building on.